Hello ladies and gentlemen, and today I'm going to be introducing our third episode. Here we will be looking at the nuclear structures of atoms and how the proton and neutron rings that we discussed in the last episode can actually be fitted together to form the various atomic nuclei. In this episode we will start by looking at how we can build the atomic nucleus of hydrogens 1, 2 and 3, as well as the isotopes of helium 3 and 4. We will then move on to the heavier elements and show how these can be built from the structures of hydrogen and helium. Lastly, we will discuss all of the different rules that need to be followed to produce stable nuclear structures. However, before we actually get on to look at these various atomic nuclei, let us just recap about these ring structures for a minute. At the bottom here we are showing you a diagram of a neutron ring which consists of these 1836 threads. The important point to notice now is the electromagnetic fields of these threads, and what we observe is that these fields sit at a 45-degree angle to the actual ring of threads, i.e. the plane of the ring. I'm pointing this out now as it becomes very important later when we start looking at how these proton and neutron rings bond together. So let's start at the beginning with hydrogen 1, which is also the easiest case as its nucleus only consists of one single proton, as shown at the bottom here. Thus its nuclear structure is very boring. It's just this lone proton ring sitting on its own in the middle of the nucleus. So let's move on to something a little bit more interesting, say hydrogen 2, since this consists of a single proton and neutron. Now these two particles are bound together because part of their rings superimpose on top of each other, as shown in the diagram below. Also, since the electromagnetic fields of these threads sit at a 45-degree angle to the plane of the ring, as I previously mentioned, then for the proton and neutrons bind together, they must be arranged at right angles to each other, i.e. twice 45. Moreover, where the threads superimpose on top of each other, this creates a region of lower energy density, and it is this decrease that is associated with the nuclear binding energy or the strong force, which we will discuss in more detail in a later video. Again, we can continue this same process of building up the atomic nucleus with hydrogen 3, which has one more neutron than hydrogen 2. This is where things really start to get interesting, because the question becomes, where do we put this extra neutron, as it can be connected either to the proton or the original neutron. These two possibilities are shown in the diagrams at the bottom. Just as in the previous slide, we're using a red ring to represent the proton and blue rings to represent the neutron, and it's this colour scheme that we'll be using throughout all of these videos. So we've got these two different possibilities for hydrogen 3. Either we can have two neutrons connected to a proton, as shown on the left, or we can have a neutron-neutron-proton arrangement, as shown on the right. Now these two different options are what we refer to as metastates, and in the case of hydrogen 3 there are two of these metastates. However, in the left hand diagram we observe that these two neutrons are facing each other, which we refer to as paired. This pairing of particles, in the case of the neutrons, implies that the left hand diagram exists at a lower energy level compared to the right hand structure. Thus the left hand structure is the one more likely to exist in nature. That's not to say that the right hand one could not exist, it would just be at a higher energy level. In fact, protons and neutrons can switch places by exchanging the extra thread located within the neutron, but this does require the emission or capture of energy depending upon whether the particles are pairing up or not. Thus, one particular hydrogen-3 nucleus could jump from one version to the other and back again, assuming it absorbed or emitted the correct amount of energy. Well, let's go on to helium-3, since this is what hydrogen-3 actually radioactively decays to. In simple terms, this decay occurs because the lone proton in hydrogen-3 is insufficient to stabilise both of the neutrons indefinitely. Thus, after a period of time, a build-up of energy occurs in one of the neutrons, and it breaks, spitting out an electron and becoming a proton, i.e. a beta decay. Hence, it is no surprise that the structure of helium-3, as shown, is very similar to that of hydrogen-3. The only difference is that with helium-3 we have 2 protons and 1 neutron instead of 1 proton and 2 neutrons. Now, these 2 protons are sufficient to keep the lone neutron stable indefinitely, and thus helium-3 is a stable structure. Furthermore, there is only one possible structure of helium-3, as protons cannot be connected together. Neutrons, on the other hand, can be connected to other neutrons as well as protons, but protons can only be connected to neutrons, leaving this the only possibility. Again, a higher energy level state could have the 2 protons next to each other, but only exist for a very short period of time due to the electromagnetic repulsion between the protons. This is assuming that the structure didn't blow itself apart before the neutron and proton switch places again. Talking of switching places, given that hydrogen-3 was in its lowest energy level when it decayed, i.e. the 2 neutrons are connected to the proton, then this would result in 2 protons being connected when the decay occurred. However, as I've just mentioned, this would quickly result in the neutron and proton switching places. And as I previously mentioned, this switching of places is achieved by the proton and neutron exchanging the extra thread located within the neutron. Lastly, although we have shown the rings existing at right angles to each other, these rings are not rigid structures, but have a degree of elasticity about them, similar to rubber bands. Thus it is possible that the neutron would actually be elongated and the protons may be bent outward slightly to increase the distance between the 2 protons, i.e. an equilibrium would occur between the elasticity of the neutron ring trying to pull it back into a ring and the repulsive force between the 2 protons. However, for ease of understanding, we've always drawn the rings of the same size and shape. The next nuclear structure after helium-3 is helium-4, as this just contains 1 more neutron, and this allows us to complete the box structure as shown. In fact, the 2 diagrams at the bottom both represent helium-4 nuclei. It's just on the right hand diagram we've actually put the box structure around the rings to make it easier for you to see exactly where all the rings are situated. They're just guidelines. So we now have this box structure, and what we find is that this box structure is the basic building block for all of the other elements, and this will become very clear later, where we will actually show you how to build up these heavier nuclei. Lastly, the neutrons within this arrangement could become elongated, similar to that as I mentioned for helium-3, due to the repulsion between the 2 protons. But as I stated previously, we've just left all the rings the same size for simplicity. This is the end of the video, but this episode does continue in the next part, so I hope that you will actually join us for that. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.